lot of graphs that I didn't want to make you have to write out every time. And even though I still printed them out, I still have a second day of notes that we'll finish tomorrow for all the stuff that's in this section. But functions and their properties. So this is a book definition of a function, right? A function from a set D to a set R is a rule that every value in the D is different, right? And probably maybe you remember to be a function, all x's are different. They're just talking about generically a set D and a set R. We've been talking about functions at least all the way back to algebra, if not even in pre-algebra you talked about what is a function from a list of numbers. We really care about equations as functions more than just sets of numbers. Almost everything we deal with in algebra and pre-calculus and calculus are functions. The exception to that is conic sections, which we will talk about. Conic sections are not functions, and you'll see that it's much harder to graph functions, much harder to graph things that aren't functions, and you can change the mode on your calculator to graph such things because it is really a lot more difficult to do. You got to know these words. The set of all D is called the, what do you think? The X's are called the, starts with a D. Domain. Okay, so that's what you put in. You put in the X's. The output values is the set called the range, right? Hopefully you know those words. If not, you need to learn them. Back in the old days when I was in whatever class, algebra, pre-algebra, I always remembered them by alphabet order. Hopefully you just know them by now, but domain is X's, range is the Y's. The big focus today for most of your homework is finding domain and range, and I'm going to hopefully give you some skills to do that if you feel like you don't know how to find domain and range. Lots of functions that we deal with have domain and range of all real numbers, right? Really nice functions have domains and ranges of all real numbers. So we're going to talk about which ones don't have domains and ranges of all real numbers, and in Algebra 2 you dealt with a lot of those. But remember that sometimes it is just negative infinity to infinity is your domain and range. Seeing a function that says of the three graphs shown below, which of these is not a function? And hopefully, maybe you feel really good about this. Which one of these is not a function? Because why? It doesn't pass the vertical line test. So who can tell me what that means? Like, what is the vertical line test if you had to explain it to someone? That's a tough question, right? So, if it doesn't pass the vertical line test, right, that means it does have the same x values, right? And so it's kind of using the same definition of a function. All the x's have to be different. So I always use my pencil, right? Your pencil's a vertical line. If you take your pencil across the graph and that pencil touches the graph in more than one spot, then it fails the vertical line test, which means it's not a function. All functions should pass the vertical line test. All right, so I kind of wrote my own little definition here. But you need to make sure that you could tell me what the vertical line test is if I asked you a question to explain the vertical line test to me. And so I said y is a function of x if and only if no vertical line passes through the graph more than once. My husband works with a guy whose daughter is taking geometry this year, and he feels the need to tell my husband all of his complaints about geometry since I teach math. And yesterday his complaint was, why does my daughter have to learn all these if-then statements for remembering geometry? You have to do if, then, inverse, converse, contrapositive. And really the reason that you do that is because everything we talk about in math is written like that. All theorems, all rules are written as if this, then this, or if and only if. And so that's why you learn that in geometry, because all the important things, all the rules of math, whether you kind of skim over them or not, of how they're all written in that if-then format. Or in this case, if and only if means you could read it in either direction. The hypothesis and the conclusion are true no matter which one comes first. So that's why we make you do all that darn writing in geometry. Okay, moving on. Domain and range. Your book kind of split this up as find only the domain or find only the range, and I've kind of squished in the words. We're going to find domain and range of each of these, right? So not just one or the other. And I started with ones that don't have a domain of all real numbers because I want to talk about like what are some key functions that you can think of that don't have domain and ranges of all real numbers. One thing you can always do is you can graph it, all right? Hopefully, we're going to learn some strategies that you can figure out how to find domain and range without graphing every time because that's not going to be very much fun. But you graphed square root functions last year. Do you remember what the shape of a square root function looks like? Or a description of a square root function? Oh, she said a v. Is a v a square root function? A v is a absolute value. Yeah, you did those. You did it in the same section, so it's easy that you would get that confused because it's the same section in algebra 2 books. It's like a line but not a straight line, right? I always say half a parabola on its side. That's my definition of a square root function because it's half of a parabola on its side. Let's pick some points here and graph this just to remind you, and then we'll talk about domain and range here. You can pick a lot of numbers for square root functions. I would pick numbers that give me perfect squares if I was doing this. So what would be a number that I could pick for x? 2 I could pick, and if I picked 2 for x, I would get the square root of 2 plus 2, which is just 2, right? I'm not going to really show my work there unless you need me to. What else could I pick? 7. Because if I pick 7, 7 plus 2 is 9, and the square root of 9 is 3. You could just keep picking higher and higher numbers here. So let's pick a little lower. What's a perfect? 1 is a perfect square. What number could I pick for x that would give me 1 under that radical? -1, because -1 plus 2 is 1. Can I take the square root of 0? What's the square root of 0? It's just 0. It's okay, guys. You can talk. Which means if I want to get 0 here, what number do I have to pick for x that would give me 0 under that radical? -2. Even if you don't know what the shape of this is supposed to be, if you can pick some points, you should be able to graph that and see what's happening here. XY chart, it's like the always go back, like if you forget what to do on the graph, make an XY chart. You always can make an XY chart. I'm going to make 7 since I have 7 on my chart here. So 2, 2, 7, 3, -1, 1, -2, 0. And hopefully you see that that's not a straight line. And by the next couple sections, we're going to review like all the types of functions that you've learned so far in Algebra 2, which means you're going to hopefully know the shape of this by just looking at the equation. But that's definitely that like curved graph. I call it half of a parabola on its side. I'm saying that it stops here, and I think we could verify that. What happens if I pick -3 or any number smaller than -2? What's going to happen? Yeah, that's going to equal the square root of -1. We can't graph imaginary numbers on here, so that means I don't have anything past here. So that's why it's just half of a parabola on its side. And I could keep picking bigger and bigger perfect squares and getting more values there. Vague memories of this from Algebra 2. So if you can make a graph, the domain and range is just looking at it and telling me where does the x start or stop, where does the y start or stop. And on this one, domain is the x's. What is the smallest x value that I'm allowed to choose here? -2, because anything less than -2 gives me an imaginary number. So I can say my domain, and again, I'm a big fan of interval notation. I'm going to say it starts at 2 and goes on forever positively, right? So I'm going to say -2 to infinity. Set notation, you would say x such that x is greater than or equal to -2. Can anyone tell me how I could have found that by just looking at the equation without having to graph that? Or do you see any correlation with our answer that we got and what's in that equation right now? Yeah, the smallest square root you can have is 0, because anything less than 0 under a radical is going to give you an imaginary number. So you just have to figure out what under the radical makes it go to 0, and that's where you're going to start. Depending on what happens outside, maybe it's going to open to the left. Might think about that. But that's going to be your starting or stopping point every time. When you see a radical, the smallest number you can have under it is 0. The range is the y values. Again, a graph's really nice, because looking at that graph, what would my range be? Or what are the only y values I have on my graph here? Is the range all real numbers? Does the graph go up and down forever in both directions? No, no, it's not all real numbers. What's not included on here? What don't I ever get? Negative numbers, which means I only get positive numbers, yes? So how would I write that? It's like pulling teeth in here today. How do I write no negative numbers in interval notation? 0 to infinity, including 0 or not including 0? Included 0. 0 to infinity. Or you could say y such that y is greater than or equal to 0. That would be set notation. Here's a big hint for you. Look at this point on my graph. The start of my domain, when I plugged it in, I got the start of my range. Not a coincidence that where the x started or stopped gave me the point of where my y started or stopped, especially in a square root equation. All right, so when I give you these today on your homework, I even wrote on the homework paper, like, you don't have to graph these. Some of the assignment says to graph, but you don't have to graph these. If you can find the domain and range without graphing, by all means, find the domain and range without graphing.
It'll always be like that.
In a radical equation, yes, always, in a square root equation. Is it always necessarily going to be bigger? No. Because what if there was a negative out in front of that radical? Now that would be flipped over, and now that would be negative infinity to 0. You still might have to think about, is it going up or going down? But yes, the y value that you get there will go with that x value. Well, let's look at this one. Again, I'm making you do domain and range. Do you remember doing functions like this last year? X on the bottom? I call these functions rational functions. The book calls this reciprocal function because the x is in the bottom instead of the top. If you don't remember what this looks like, guess what we can do? Good old XY chart. And again, that's a really smart thing to do if you forget, because when you make a few points, hopefully it'll come back to you. What happens when I pick 0 for x? What's 2 divided by 0? Not 0, right? Not 1. Do it on your calculator. What does it say? Your calculator might just blow up if you do it on your calculator. Oh. You can't divide by 0, right? You can't take something and divide it into 0 parts. It's undefined. Really, really important later when we come back to our domain, that's undefined when we plug that in. So which means when we plug in 0, we get nothing. If I plug in 1, I get 2 over 1, which is 2. If I plug in 2, I get 2 over 2, which is 1. I can just keep picking here. 2 over 3. And you can think about what's going to happen as you keep picking numbers there. You're just going to keep getting fractions, right? If you picked 100 here, you would get 2 over 100, which is 1 over 50. So even if you went all the way out to 100, you're just going to get this small fraction here. What's going to happen when I pick those same negative numbers? If I pick the same numbers negatively, what's going to happen with my y values? They're just going to be negative. So let's graph that and see what that looks like. Zero, I got nothing. At 1, I have 2. At 2, I have 1. At 3, I have 2/3, and it's just going to keep getting smaller and smaller and smaller. So like this side, I think is just going to go down like this. Actually, I don't think it's even ever going to get to 0. No matter what I plug in there, 2 over 1,000, 2 over 1,000,000, it's still not 0. It's just a really small fraction. Think about what would happen if you picked a number between 1 and 0. Like, I'm running out of room here. I'm going to make it a very small chart. If I picked 1/2, you would get 2 divided by 1/2. Dividing by a fraction is the same as multiplying by its reciprocal. So that's really just 4. So like if you plug 1/2 in, you're actually going to get 4. When you divide by a fraction, you're actually flipping it over. So like this side's going to go up like this. Remember graphing things like this? I always describe this graph like this. That's my description. Because it always has those two shapes there. And we're going to get the same thing when we plug negative numbers in. They're just all negative now. So when I plug in -1, I get -2. When I plug in -2, I get -1. If I did -1/2, I would get -4. I'd get, what's over here, -2/3, right? The exact same shape, only flipped over like this. They're supposed to look exactly the same, like, kind of don't. Okay.
Is it ever supposed to touch the line?
It's really not. I mean, my picture kind of looks like it. If you graph it on a calculator, it's going to look like it. It's going to get really, really close to it, right? So as long as it's, see, like up here, I kind of made it look like that it touched it. Just kind of, it just ends up like almost right on it. 2 over 1,000,000 is so close to 0. Kind of hard to graph it without it almost looking like it touches. But it should never cross the line. All right, it's just getting closer and closer to it. Right? Those are called asymptotes, when you have a line that your graph's getting closer and closer to, but it never actually gets there. This is an example of a graph that has both a vertical and a horizontal asymptote. So that's another big thing. Domain and range is not going to be all real numbers if you can get imaginary numbers, like on square root problems. If you have fractions that have x in the denominator, you're going to probably have an asymptote there, which means you can't have a domain of all real numbers if there's an asymptote. So I think the easiest way to find domain is tell me what x can't be, and your domain is everything else. So what's the one number that we can't plug in here for x? 0. Right? It's undefined. So my domain is everything but 0. And this is when people like set notation better than interval notation. To set notation, we could say our domain is all x's except x can't equal 0. Right? You can just say it. It's everything but 0, because it's going to go forever in both directions, but it's never going to touch 0. Interval notation, you have to do the 2 intervals. You have to like skip over 0. So if you were going to do this in interval notation, you would say -∞ to 0, skip over 0, So union 0 to infinity. So we just jumped over 0. We didn't include it. We used parentheses, but every number other than 0. And again, I'm okay with both notations. You just have to make sure you're doing it correctly, which one you're doing. The range is what can y be? Y is definitely going up forever, and it's going down forever. If we use my rule, Maddie, that I did last time, what happened when we plugged in the one number that x couldn't be? What happened on my y value? It was undefined. So could we kind of use that same rule on the last one? Can we ever get this equation to equal 0? We can't, which means there's also a horizontal asymptote, and you learned some rules of that last year, and we'll go through them again eventually in this chapter of how you can tell the horizontal asymptote. But that means the range is exactly the same as the domain on this. The y can't equal 0. But if you're going to write that in set notation, you have to use y and not x, right? Domain and range stress people out, but we're really just trying to think about what is allowed to be for x and what is allowed to be for y on those graphs. I threw the next one in there just to remind you that we know a lot of functions domain and range without having to stress about what it can't be. X in the denominator, can't have that. Negative under a radical, you can't have that. But look at the next one. Find the domain and range of this function. This is just a lovely polynomial function. There's nothing crazy happening here. There's no x's in the denominator. There's no radicals. There's no asymptotes, which means what is the domain and range of every polynomial function going to be? Is there anything x can't be in this problem? Is there any number you're not allowed to plug in for x? It's all real numbers. Yeah, it's a polynomial. So we like polynomials. They're nice smooth curves. I don't care what it looks like. I know it's a smooth curve. I know it's going to, right? It's going to be something nice. X is going to go on forever. Y is going to go on forever. I really know because it's an odd polynomial, but the arrows go in opposite directions there, that it's going to be all real numbers. So the domain is all real numbers. The range is all real numbers. All right, so just know that that still happens. All right, I tried to pick some harder ones to do with you because it's much harder to do the ones that aren't all real numbers. Okay, that's the hard part. The rest of this is a lot of pictures and words, but hopefully the rest of this isn't as stressful as domain and range is. Continuous functions. All right, I really like, I don't know if this book defines it the same way that the calculus book does, but the calculus book defines a continuous function is a function that you could draw without ever lifting your pencil. It's a great definition. A function is continuous if you could draw it without ever lifting your pencil. So like that lovely polynomial function that I just gave you is a continuous function. A discontinuous function is one that you have to lift your pencil up, and there's different types of discontinuities. All right, so I have different ones here, right? This one, there's a little hole right here at A, and then there's a little dot up there that's actually going to be like a piecewise function that we'll talk about later. But this is actually called a removable discontinuity. And the definition of a removable discontinuity is it could be filled in with one point. Basically means if there's a hole in your graph, that's removable because all you have to do is fill that one hole in, and then now it's continuous again. If we could just take that one little black dot and move it down, we now had a continuous function. This is also removable, right? Those two go together. You might say those are the exact same graph, but the difference is this one has the dot up here, and this one doesn't. This one's the easiest to remember because it has like a break in it or a gap in it or a jump, right? and that's the name of it. It's called a jump discontinuity because there's a jump. You stop and you have to jump up to the next point on your graph. And then if your graph has a vertical asymptote, it is not continuous at that vertical asymptote. And we call that an infinite discontinuity because it goes on forever, right? It's not just a jump. You can't just jump from one part to the other, like it goes forever up. So parts of your homework today are just going to talk about, is it continuous or not continuous, and where is it continuous or not continuous, just to practice kind of using these words. We really like continuous functions. Most of the functions we deal with are continuous. So the next one's really silly. I don't know why they gave such a silly example, but also it might be hard to see on your paper. But it says, which of the following figures shows functions that are discontinuous at x equals 2? And again, hopefully you see this one over here that we could draw without ever lifting our pencil up. But this one, we have that little hole there that we'd have to pick our pencil up and move to the other side. So this one is not continuous or discontinuous. So that may be some new vocabulary. And then the last thing really I want to talk about today is just increasing and decreasing and maxes and mins. Again, words I know that you use, just kind of reminding you what those mean as we go through here. So I put some blanks for you to fill in so you didn't lose all focus here. It says a function is increasing if for any 2 points in the interval a positive change in x results in a positive change in y. So as x gets bigger, y gets bigger. I always think about increasing, like looking at the graph, like from left to right, like it's going up, right? Like if you had a graph like this, definitely increasing, because I always think about, look, like he could just walk up the graph, right? It's going up. That's how I think of it. But the technical way is as x is getting bigger, y is getting bigger. So that means that a decreasing function means that as x gets bigger, y is actually getting smaller. Again, to me it's a visual thing, but I don't know if everyone sees it that way. But if you're looking at your graph from left to right, it just looks like your graph is going down. So like, I'm just going to draw linear here for now so you can see that that's a decreasing function. And if there's no change, as x changes, y doesn't change, then the word we use there is constant. And again, we can talk about slope here for all of this. Positive slope, negative slope, zero slope. Y doesn't change. So on the next slide there, I just gave you some pictures of talking about how to say whether it's increasing or decreasing. On what intervals is it increasing or decreasing? That's what's going to be on your homework today. And so looking at this graph, they don't really put arrows on this, which just really kind of bothers me. So it's kind of, you can give two different answers on this, whether you want to say that it stops right there, or whether you want to say put arrows on it and it goes on forever. But for this graph, do you agree that it's going up the whole time, like it's increasing the whole time? And so you could say it's increasing on the entire interval. Oh, I wrote it there, I have a little increasing. You could say it's increasing from -5 to 5, if you wanted to say it stops there. Or if you wanted to say, let's put arrows on it, you could say it's increasing from -infinity to infinity, would be the other alternative there, depending on how you want to read that graph. This is an example of a function. Again, if we look at it, as x is going, y is getting smaller here. So this one is decreasing on its entire interval. And again, when you give me intervals, you're giving me x values, right? So where did I get this -5 to 5? I'm looking at the x-axis. That's what I'm giving when I'm talking about intervals here. Again, I like to think of it that it's decreasing on its, like from -infinity to infinity, because I like to think about that it's going forever, that it's not stopping, but I'm kind of okay either way you want to do it. And this one is constant because it doesn't change, it's just a straight line. What you're going to get on your homework is more of a combination of telling me when does it change from one to the other. And so this is a really cool graph here. And we could say it's decreasing from here to here, right? So let's see how they wrote it. Yeah, so they didn't put arrows here, but they're saying that this goes on forever. So it's decreasing from negative infinity to -2. And there's always a big debate in math of what's happening exactly at -2. Like, do you include 2 with a bracket, or do you put a parenthesis around it? And the answer is I would count either one. As long as you stopped it at -2, whether you put a bracket or a parenthesis around it, I would count it. Math people have decided that you should put brackets around them, because up to that point in that direction, we would say it is decreasing. I understand the conflict there, because you think, how can it be decreasing and constant at -2? So I'm okay if you use parentheses too. But constant from there, and then it changes to increasing. So that's what I want to see on your homework, is like that you give me the different intervals on that. Questions about that? All right, look at the next one then. That's what I asked you to do on the next one. It says, given x squared over x squared minus 1, tell the intervals on which the graph is increasing and which it's decreasing. So a little bit uglier than the one I just gave you, because there's these lovely asymptotes here. You're giving me x intervals here. If there's an asymptote, you're going to have to skip over that, because that asymptote's not included in the graph itself. So maybe you're not sure where the asymptote is by just looking at this. That's where using this equation is helpful, because if I said, what can't x be, I think it's going to be at -1 and +1. I'm going to have an asymptote there. So you have to keep that in mind as we're doing this. Increasing, decreasing. I don't think I have any constant. Do you agree with that statement? So I like to start at negative infinity, all right? Negative infinity. Oh, wait, I should have said that. Oops. If I start this way, is that increasing or decreasing? Increasing until when? Yeah, that asymptote is a break in that graph, so we can't include that. It's not in the domain. So we have to say it stops at -1 because it skips over it because of that point of discontinuity. Because it's a discontinuity, I'm going to put parentheses around it. -1 is not allowed in this equation because it's a discontinuity. So then I jump down here, and what happens on the other side of -1? Is that graph increasing or decreasing? Until 0. So I can say it's increasing from -1 to 0. Notice that -1 is the start and the stop, but because it's an asymptote, I have to skip over it, just like I did when I was writing my domain and range earlier. 0 I'm going to include just because it is part of the graph. And then what about for the rest of it? From 0 down to the next asymptote, do you see that that's going down? So that's decreasing. So I'm going to say from 0, and I got to stop at that asymptote again. And then I skip over the asymptote, and that's also decreasing. So I would say from 1 to infinity. You could use the unions if you want there, but they just ask for intervals, so you don't have to. Like, we're not really writing a set as a solution, so that's why I didn't use the unions. But I wouldn't mark you wrong if you didn't use unions there. All right, last one, just some vocabulary again that hopefully maybe we talked about last year, maximums and minimums. There are 2 types, though. There is a local or relative maximum minimum, and there's an absolute maximum and minimum. So a local, aka relative maximum, is just a high point on the graph, a turning point on your graph. And it occurs where the graph changes from, you have a maximum, it's going to change from increasing to decreasing. So anytime your graph has a turning point where it changes from increasing to decreasing, that is a local maximum. And we could say the same thing about a local minimum or a relative minimum. Except for a relative minimum, right, that's a low point on your graph where that's going to change from decreasing to increasing. Those are really, really important when we get to calculus. But just because your graph has a turning point does not mean that it is the absolute highest or lowest point. So that's the difference between absolute maximum and absolute minimum. So an absolute maximum is the highest point. Oh wait, there's no hidden thing there. I have to write it. The highest point on a graph. What do I mean by that? If I had a graph like that, that is a local maximum, but there is no absolute maximum because that graph just goes on forever. The same thing with an absolute minimum. A graph might not have an absolute minimum because this graph has a local minimum. It's a turning point. It's a low point on the graph. But this graph keeps going down forever, which means there is no absolute minimum. And so just want to make sure that you know those vocabulary terms as we go forward here. Okay, so there's a whole lot of stuff in this section. This is not even all the stuff in the section. And so we'll continue that tomorrow, which is why on your assignment sheet there are 2 days of homework. So if you look at the assignment sheet, it's listed twice because there's 2 different days of homework on this. So today there's a lot of domain and range stuff. If the directions say graph or check graphically, that means they're assuming that you all have graphing calculators, and we don't all have graphing calculators, which is why there is no expectation that you have to graph all of those. The expectation is finding the domain and range using algebra. And so we'll talk about some of those tomorrow. If you have a calculator and you want to look at some of them, you can to help you kind of check your answers. There's free graphing calculator online. There's lots of free graphing calculator apps for your smartphone if you want to get one. I have one called Good Grapher. It's a really good one. It was free, or I could buy it for 99 cents to get extra stuff, but I just did a free one. So if you want that, but just know you do not have to graph, so kind of ignore those directions on these. I'll always tell you if you do have to graph. But when it says check graphically, it means with your calculator. Okay? Don't forget about test corrections and the retest and active laser stuff if you are still needing or wanting to retake that. So I found this calculator in here. What's this form? Give me one.